has started. So we are now recording. Okay? As I just said, today's lesson we start off with thinking about how waves behave, what waves do in certain situations when they're on their own, when they encounter certain kinds of media or whatever, but then also what happens when they interact with one another, when two waves come together. That's where we're going to eventually end up. Yesterday, we looked at a lot of these things in action in the Slinky and what we do with the Slinky. Who was holding the Slinky yesterday? I can't remember. Sean was holding the Slinky. Okay. All right. So, Sean, first thing we did, right? We took the Slinky. I shook it on the one end. That wave, the disturbance creates a wave. It does work. I did work on the Slinky. Wave travels down to your hand. What happened when it hit your hand?
Changed sides and came back to you.
Changed sides, went back the other direction. Did it transfer energy to you?
Yeah.
Did your hand move?
Yeah.
Little bit, right? But did all of the energy of my shake end up being transferred to you eventually?
No.
No. Okay? There are certain times when a wave is traveling through a medium that it just can't pass the energy on from one place to the next. So remember we kind of said that if we talk about quote-unquote the wave, right? If there's just a section of people that don't want to do the wave, what's going to happen? It's going to stop, right? Now, just because a wave may encounter a medium where it can't pass through doesn't necessarily mean the wave is going to stop, but it will bounce off. So reflection is that situation where a wave is traveling through a medium and it encounters another medium. And for whatever reason it is, it can't pass through into that medium. So what happens? It bounces off and starts going back in the other direction. Okay? It will bounce off at exactly the same angle that it came in at. Now, Sean, when we did yesterday's demonstration, right, those waves were coming directly at you, right? Okay? So they bounced off directly off of you. But if they were coming in at some angle, we would see that they would come in at a certain angle and then bounce off at a certain angle. Very similar to like when you're playing pool or something like that,
Pong.
right? What?
Pong.
Or Pong, right? If you still have a Pong machine, right? Pong would be like the original video game. Yeah, it's like the two paddles on either side of the screen, and there's just a little ball that goes back and forth. At the time, that was like that was like Call of Duty 4. I mean, that was like that was it. I mean, that was like, I mean, people. Not that people did that, but people would like, it would be the equivalent of people waiting outside of the video game store. Like, Pong 2 is out. Now there's two balls that you have to keep. But anyway. But like so if you're playing Pong or if you're just playing like good old-fashioned pool, right? If you have to like bounce the ball off a wall, right? You can figure out how it's going to bounce off the wall based on how it comes into the wall. We would say when you get into AP physics or physics and you start talking about mathematically analyzing this, we would say that where's my pointer? There it is. The angle of incidence, that's the coming in angle, is equal to the angle of reflection. Okay, so it comes in and goes out at the same angle. All right? Now, let's talk about that reflected wave. So, we saw yesterday that when that wave bounced off Sean, was it basically the same wave? Yeah, there were a couple differences, but it was pretty much the same wave. Reflected waves have the same speed, frequency, and wavelength. But as we saw yesterday, they might be flipped over, depending on the kind of reflection that occurs. But they have the same speed, they have the same frequency, and they have the same wavelength. Why? It didn't transfer energy to whatever it was bouncing off of, so it's still just what?
Same way.
It's the same wave that I made, it's just now traveling in the other direction. Example, an echo, right? When you hear an echo of your own voice, what does it sound like? It sounds like you, right? but it sounds like you. Why? Because it is you, right? It's the same wave that you made that just bounced off of something and came back to you, and now you hear it. It's kind of like hearing yourself on recording, right? It doesn't sound exactly the same to you, but to everybody else, it sounds exactly the same. It's just you. Why? Because it is you. It's the same wave, all right? But what other change happened as we saw that thing go back and forth and back and forth? Sean?
The amplitude lowers.
The amplitude decreased though, right? Amplitude is usually lower. Why did we say the amplitude is decreasing? Sean, go ahead.
Some energy was transferred.
Some energy is being what?
Damped.
Converted into what, Paige? Thermal energy, and we call that damping, all right? Friction, as this wave travels through the medium, is causing some of that energy that I originally gave to the slinky to be converted into thermal energy. And that causes the amplitude of the wave to decrease. And we call that damping. All right? Good there? So that's reflection. All right. Questions about reflection? Okay, let's talk about the next wave phenomena. Starts with an R, but it's refraction. Okay. Have you ever seen that, this little demonstration or whatever, you can see it like with flowers in a vase, or if you like put a pencil in water in a glass. It doesn't look like it's connected, right? It looks like it's separated from one another. Does the pencil really change when it goes into the water? No, but how we perceive it does change because of this idea of refraction. Refraction is defined as the bending of a wave caused by the change in speed as it enters a new medium. We kind of saw refraction yesterday, or at least this part of refraction, the change in speed as it enters a new medium, right? Towards the end, what did I do with the two slinkies? Kind of put them together, right? What happened when the wave got to the boundary between the two slinkies?
Bounced back, but also kept going.
Some of it bounced back, some of it kept going, right? So it's split up, and we'll talk about that in just a second. What happened to the part that kept going into the new slinky?
It wasn't as big and strong.
It wasn't as big and strong, but more specifically it what? It slowed down, right? There was a change in speed as it went from one slinky to the other slinky. Because like we said, the speed of waves depends on the medium. What does it travel through? How easily is the energy transferred from one part of the medium to the next part? Ryan, go ahead.
Could it get like faster too?
Could get faster, depending on which medium we go from and which medium we go into. If Sean would have created the waves in the small slinky, when they went from the small slinky to the big slinky, we would see it take off, right? Hold on a second. Maybe I'll come back out in a second. They're doing it now, so I was, if they were at that part, I was going to show you. But yeah, right. We could see an increase in speed just depending on what medium we go from and what medium we go to. Okay. But if the angle is right, we will see that it looks like that wave bends as it goes from one medium to the next. How many of us have the unfortunate circumstance at home that we are responsible for cutting the grass?
Oh,
Anybody?
That's fine.
3 people. That's it.
That's because I'm
Not to be sexist, but this class really is like 2/3 girls.
I used to, but my parents don't trust me to ride along.
James, what's wrong with you?
As like,
I'm mowing every time I stay. How can you be a guy and not have to mow the grass?
Alright, so,
Yeah, I do a shirt.
alright, so,
Everyone walks.
so basically you used to cut the grass, but your parents don't trust you anymore, is that what it is?
Yeah.
I suppose there's something to be said for that, if you do like a really crappy job, your parents probably won't make you cut the grass
Or if
anytime.
you like
but,
cut
you
your
know.
foot off.
I know.
that's true.
Unfortunately, I can't do that because I can't like make my daughter. I can't make like my 5-year-old daughter do it. So.
Go, push the
But anyway,
It's still got a little pole, so
so have you ever had that situation? Sometimes it happens like if you've never cut the grass before. Just imagine for me. Okay. It happens kind of a lot in the spring when the grass like grows really fast and gets really tall and it's like nice and green and thick, you know. And you're along the edge of the grass, but you got one set of wheels on the sidewalk, but then the other set of wheels in the grass, right? What starts happening to your lawnmower?
you don't get it straight.
It doesn't go straight, right? Because why?
One set.
Cause
of
it's on
wheels.
two.
One set of wheels are doing what?
Well, one thing is like has more friction,
Right. So that means one set of wheels is going,
faster.
and the other set of wheels is going,
Slow.
and now we don't end up with a straight line. That's kind of what happens with refraction, is that the wave, one part of that wave is moving at a certain speed, and another part of the wave is moving at a different speed, and that causes it to look like it's bending. Because one part's going faster than the other part. Same way. Say again? It happens with all waves. It does happen with light waves, but it happens with sound waves as well. We don't usually see it as or hear it as much with sound waves because we only pick up a sound wave when it gets to our ear. What it did before, we really don't have any idea. And that's kind of the thing with light waves too, and we'll actually see that in just a second. But you'll hear in a situation like this, if we can follow the light wave the whole way, we can see that, yeah, it was traveling this fast, but when it got to the glass, especially with the way that it hit the glass, the angle that it hits the glass plays a big role in this. That in this one, so like saying with this one in the middle, right, there really is no bending of it. Not because it didn't change speeds when it went into the glass, but because it hit this glass straight on, we really didn't see any bending. It's more if you hit it at an angle that we see the bending part. Ryan, go ahead.
If you were like underwater and you heard someone talking above the water, would the sound be refracted?
Yes, although once again, like we said, you wouldn't know that it got refracted because you only hear the sound wave as it got to your ear. You know, so you wouldn't know that it did. But yeah, if it went from one medium to the other, it did change speeds. And there was a bending, especially depending on the angle, right? But you don't really know that. Here, an example, all right? So let's draw a picture. Ooh, got that one. Picture time. All right, so let's get ourselves a blank sheet here, okay? So this is like getting us ready for some better times, okay? Here is the edge of a pool, okay? And here's the water, okay? And
Put the vacuum at the bottom.
here is you looking all tan. Yeah. No, this is your friend who forgot to put sunscreen on. Yeah. That's you, Sam.
Why are you wearing
Because it's skinny dipping. That's
All
how
right.
you do it.
So let's talk about this idea of refraction and how it doesn't just happen by itself. Okay? So you're sitting on the edge of the pool, and here, right? Here's the big sun up here in the corner, right? Okay. And the sun sends out light waves, right? And these are yellow, right? And they hit the edge of the water. Now, what happens to some of those light waves when they hit the edge of the
They
water?
bounce off.
They bounce
Which
off,
is why it's
right?
shiny.
And you get that big like flash, right? And it hurts your eyes. And just like we talked about, the angle that these sun rays come in and the angle that they go out is exactly the same. And if you're a little bit taller, okay, there you go, right? Then you see those light waves coming off of the water, and it's all bright, and there's that big glare, and it hurts. Okay? Now, that's reflection. Okay? This is light waves. So Sam, this is an example. This example uses light waves, but it happens with all kinds of waves. This is reflection, just light waves bouncing off the surface of the water. But do all light waves bounce off of the surface of the water? Okay? We talked about that yesterday when we saw the two slinkies. What did we see happen when the wave got to the boundary of the two slinkies? Some kept going, but some bounced back. This is the bouncing back one, right? But some, let's say it's red, okay, because red light is part of sunlight, and we'll learn that later on, right? Okay. So you got these red waves that are coming out, okay, and they hit the water. And instead of bouncing, they keep going, but what's going to happen when they go from the air into the water? They're going to refract. They are first. If they go from one medium to another, what happens? In this case, they slow down. But more generally, it changes speeds. Okay? And it slows down. And because it slows down, it looks like it bends. And there just so happens to be one of those nice red diving rings down at the bottom of the pool.
So it makes it whole.
Say again?
It makes it hot because the sun is hot. Okay, like if you, like if it had it, what? Why not? It would take like hours.
Yeah, they
Okay,
haven't
well,
noticed
what?
temperature.
No, it definitely makes it hot. Because like in the snow,
What?
did you see?
I'm talking about it, right?
Oh, if you leave the if you leave the ring out like on the side of the pool
No, in the water.
in the water, would it heat up the ring?
Eventually.
Eventually, but it would only heat it up to the temperature of what?
The water.
Of the water, right? Because really, Sam, the energy from this wave is going mostly to the
And
water.
it's getting conducted
Right.
from the water.
It's getting conducted from the water into the ring. So it would only ever get as hot as the water does. Okay? But if it was out like on the side of the pool, right, it could get warmer because the temperature of the air is a little bit warmer, blah, blah, blah. And actually, it would get direct radiation from the sun because waves and stuff like that. We'll get that in a second. Okay? But for this instance, so we got this stuff that came in, and now it's bending. All right? Actually, here, let me do this. I'm going to do this. We're going to follow it along that same path. And then it bends, and it hits this nice diving ring. But do those light waves travel through the diving ring? No. So what do they do when they hit the diving ring? They bounce off. And they start heading back in this
And
direction.
that's when you can see it.
And then, but now when it goes from the water back to the air, what happens to the speed?
It speeds
In
up.
this case, it actually speeds up. So it will bend again, and it will end up going here. Okay? Now, here's the tricky part about refraction. Remember the first example that I gave you, the whole idea that when you stick flowers in a vase of water or a pencil in water, what does it look like?
Bigger.
It looks weird. It looks like the bottom and the top of the flowers or the bottom and the top of the pencil aren't together. So Sam, going back to your example before about can we like notice refraction? Your eye gets this light and it says, ooh, look, red diving ring, right? So if you go to jump in the water to retrieve the red diving ring, it's not where you think it is. Because your eye works backwards and goes, okay, the ring, I'm seeing it along this line, so, oh, it must be here. Okay? Because, Sam, like we said before from your question, your eye doesn't know that it refracted, like now your brain knows because we just learned about it, but your eye doesn't know that. It just sees the light and goes, oh, it must be right there. So you dive in the water to go get it, but it's not there. It's behind you. Because that light changed speeds as it was going through these different mediums, and it ends up getting to your eye from a direction that really isn't where the object is. So like if you ever get stuck on a desert island like Tom Hanks and Castaway or something like that, you know? Everybody seen Castaway?
When you try to spear the fish.
Yeah, like if you're like spear fishing Don't aim at the fish. It's not there. Right? Aim in front of it.
That's what happened in Hatchet.
You know, so.
And he figured it out and then he was getting all
I don't think I even finished that book.
Alright. Are we okay with this? So, going back to this, okay? At a boundary between two different media, okay? I don't know if I actually got you the words for this, but the picture shows up, right? Okay? At a boundary, first, some of that energy bounces off, right? That's the big glare from the sun that's coming off the water. That's reflection, okay? But some of that energy passes through the boundary, but it changes speeds. It might speed up, it might slow down, depending on what medium it's passing from, what medium it's going into. That's the whole refraction idea. Now, what did I do? Okay, there we go. Now, if the light is coming straight down, will we see refraction? No. Refraction only happens if we're going at angles. Okay? It's like in the middle of the day, right? It doesn't really work. You don't see it as quite as bad, right? Because the sun's sort of right overhead, blah, blah, blah. It also depends on where you are in relation to the water. But if we looked at, going back to my picture, if we look at the energy from the sun here and the energy coming from the ring, we would find out that it doesn't totally add up to the energy that came in. Because what happened to some of the energy?
It turned into heat.
It went into the water and turned into thermal energy. So it goes to heating up the water. We call that absorption, or absorption, however you want to say it. Let's emphasize the P, the absorption. Okay. But all three of those things happen when a wave reaches a boundary. And we saw it yesterday in the lab, right? Some of that wave when it hit the two slinkies, some of it bounced off, some of it went through, and some of it just gets turned into heat. Okay? But that's what happens when we get to the boundary of the two media. Okay? Alright. Good? Good with that?
Yeah.
There's some other parts on your slides that kind of has some space there. Don't worry so much about those. Those are higher level concepts. But this stuff you should know. These three things you should know here. All right. Anybody that wants to write this down? Okay. Good there? So let's talk about the next one. The next wave phenomena that we talk about is diffraction. Okay. So here's a picture. Looks kind of cool. These waves are being made back here, and they're coming. And these dark spots right here represent a wall, but there's an opening, and those waves go through the wall. But you can kind of see that once they go through the door of this little wall here, they like spread out. Okay? A practical example of this would look something like here. Okay? So here's a hallway at school. And here's another hallway at school. And you either have to turn left or right. You can't go straight because there's a wall there. Okay? So this is like one of the first couple days when we get back from school, right? And here's you and your tan self, right? Okay? And then there's your miniature friend who didn't wear sunscreen all summer, right? So, No names, please. Alright, so miniature friend is talking to you, okay? And they're sending out sound waves, and they bounce, and they go here, and they bounce off this wall, right? And what's going to happen to them when they bounce off that wall?
It's gonna
Gonna come right back to you, okay? But here's your other friend, okay, who, I don't know,
I'm a little
blue,
Smart.
this is your friend Smurf, okay, is here, and you just happen to be saying bad things about your Smurf friend, okay, because you didn't know that they were around the corner. Not that that's a good excuse. You shouldn't talk about people just because they're not in the room, okay? I mean, like, not that we should, make fun of Eric or anything, because he's not here, right? That's not nice. Okay?
Watch this.
Oh, he's gonna watch the recording. Oh, let's be serious. Is Eric really gonna watch this recording?
No, he does. He told me about like.
Really?
Yeah.
All right.
So what's
I guess now we'll have a check to see whether he actually does or not. But your Smurf friend gets mad at you later in the day because he or she, it's either one of many male Smurfs or one female Smurf, heard you talking about them. But according to this picture, should your Smurf friend have heard you talking about them? Those waves went out, they bounced off the wall, they came right back. Okay? But what we find out is that when waves hit a boundary, right, remember, waves are energy. Energy, energy, energy. Once it gets to this point, just like in the picture, that energy starts spreading out. So even though you might not be in the direct path of those waves, you'll still be able to hear them. Will they be as loud as if you're right in the path? Because, right, this line right here represents a certain amount of energy. But once we get to here, right, what's happening to that energy?
It's getting spread out.
Gets spread out, right? And if it gets spread out, the amplitude of those waves is lower. And for sound, that means it's not quite as loud.
Then it also bounces.
Okay, and then it also bounces, right, and starts getting spread out and stuff like that. This is the idea of diffraction. Diffraction is the bending of a wave as it moves around an obstacle or passes through a narrow opening. Sorry, that space is pretty small, I apologize, but I wanted to fit it all on the same page so you didn't have, Alright, is that good?
Yeah.
Alright. The next one, superposition, relates to the stuff that's on the back, so I think this would be a good time for us to stop. Hey, good job on recording class today. Well done.
Yes, 2 minutes. Cool.
It's a rip in my binder.